Hi, and welcome to our program today. My name is Paul Bemis, and I'm going to be hosting a very fascinating discussion about the role of HVAC systems in the transmission of COVID-19. I have a couple of distinguished panelists with me today. I'm thrilled to have. This is going to be an information-packed session. We're going to use a lot of multimedia here, so bear with us because it doesn't always work perfectly. But before we get started, a little bit of housekeeping. I am going to be taking questions. You in the audience are in listen-only mode, which means in order to ask questions, you need to use the little chat panel that comes inside of the GoToMeeting little panel that is there, or the GoToWebinar panel that is there. So I'm going to be monitoring questions throughout this whole session, and we will try to stop and answer questions as we go. That's the best way to transmit information. However, it does get challenging, so we'll do the best we can. So with that, let me get started. I would like to first introduce my panelists. Jonathan Kay is with us today, and I'm thrilled to have him. He's a Toronto-based book author, columnist, editor. He is doing work for a publication called Gillette, which is where I first met him. He also graduate mechanical engineering, McGill University, worked in computer modeling and fluid flow and thermodynamics. Hi, Jonathan, welcome to the program.
Hi, I hope people can hear me. Thanks for the introduction.
Yeah, we hear you perfectly. I'm also real thrilled to have Dennis Knight with us. Dennis has had 40 years in the design, construction, operation, maintenance of high-performance buildings. He's a member of ASHRAE. He's currently on ASHRAE's Epidemic Task Force, which is why I reached out to him. He chairs a technology council of the ASHRAE BIM Multidisciplinary Task Group, and he's the founder of a company called Whole Building Systems. Welcome to the program, Dennis.
Oh, thank you, Paul. Thanks for the introduction.
So a little bit of background and history here. The current model of this disease and transmission dates back to, it's under a fellow named William Wells, and he did work on tuberculosis. And he basically categorized this whole issue of transmission based on the size of the particles coming out of, for example, a sneeze or a cough. And he had a cutoff with a level of 5 to 10 micrometers. And that's really where we get today the CDC's guidance on distance is based on this work done back then. So the current science on this is fairly old. Now, recent work has revealed that coughs and sneezes are really multi-phase turbulent gases. And they're very influenced by the environment in which they're in. I mean, moist air, warm air, humidity, all affect these things quite dramatically. And the lifetime of a droplet can be from a fraction of a second to minutes. And the distance can extend quite far. The distance is 23 to 27 feet based on the turbulence and the speed of the gas cloud. Exit velocities during a sneeze can run as high as 100 feet per second. They're influenced by temperature, humidity, and airflow. And once evaporated, they can, the nuclei, the small part, can stay in the air for hours. To illustrate this, I'm going to use a little multimedia. Again, we're taking some risk here with multimedia, but what I'm going to do is to show you this in some slow motion here. And I'm going to do it intentionally. I'm going to drag my screen over here, and I'm going to show you this piece. This is coming from MIT. One of the people that's done a lot of work on this is a woman named Lydia Bavera. And Lydia she's also McGill University, as Jonathan is, and has done a lot of work on the combining of fluid dynamics and fluid mechanics and mathematics with epidemiology. And she's studying this effect and using mathematics to describe it, and has pushed this a lot further than many. Not the only one doing it, but MIT's doing a lot of great work in this area. And you see here, this is a sneeze. This is a sneeze event. We're using a camera, 2,000 frame per second camera over a period of about a quarter of a second. And you can see the aerosol here going into this atmosphere. There's the sneeze, and then we have a lot of particulate in the air that's going around there. And that is of primary concern to us. This is at 110 centimeters. Now, if we back out to 7 or 8 meters, you can see that cloud forming. And particularly as the humidity drops, this material dries out. And when it dries out, it becomes more airborne. It becomes an aerosol. So this is from Lydia's work. It's referenced here. She is doing some interesting work. If you have a little time, it's really worth going to have a look at that. There's her link right there to her primary location at MIT. She's got some TED Talks there, fascinating stuff. Now, I talked to her about sneezing and coughing, but there's also work being done on just talking. Talking seems to do it as well. And so, and this work actually, Jonathan, you made aware to me. This is some NHK work done, and I clipped just part of this video. And what they're doing here is showing two people sitting close to one another, and all they're doing is talking. Again, high-speed camera. They're talking, you know, quite intensely. And here again, we're going to use a high-speed camera to show what's coming out of their mouths as they talk. Lots of microdroplets when they talk loudly. And again, it becomes airborne. Now, there's no air movement in this room. This is a still room. They're in a laboratory. But you can see a lot of these particles just going everywhere. And that's of concern. That is primarily what we're concerned about here. Now, Jonathan, part of the reason I asked him here, I read one of his articles in Gillette about super spreader events, and SSE is a super spreader event. And he took a look in the research, did a lot of great digging. It took him some time to do this, and I'll ask him about it in a moment. He looked at 54 super spreader events that he could find. There were greater than 9 linked to religious services or missionary work. 19 involved parties, mass attendance, funerals, weddings, engagements. 5 were funerals. 6 were face-to-face business meetings or conferences like the Biogen conference in February that became quite a topic. 38 of the 54 involved one or more of these activities where people were together, funerals, festivals, weddings. That's a 70% ratio, and he did not include the 5 super spreader events that were on 3 cruise ships and 2 warships, the most obvious being the Eisenhower that we all learned about. They all have the same behavior: close, extended range, face-to-face, crowded, socially animated places. Did I summarize that okay for you, Jonathan? You think that covered it? Or?
Yeah, that's the substance of it. That's right.
Now, it was difficult for you to find these events, correct? I mean, this isn't well documented as far as I can tell.
So I was surprised by how little documentation there was, and what I found was that many of the specialists in this area, virologists, epidemiologists, and public health officials, are either interested in what is happening at a microscopic level, which is like at the level of nucleic acids and genomic sequencing and you know, enzymes and receptors and stuff, or they're interested in national scale epidemiological data, like what's the fatality rate and what cities is it spreading to. But in terms of the nitty gritty of like how is this spreading in rooms, among people, among friends, what are the mechanisms? You know, getting empirical data to support this 6-foot distancing, should it be 10 feet or 3 feet? Or everything was very vague, and there was very little published research. And this is consistent with when I looked at the scientific record, there's actually been very little research since the early 20th century on basic things like how disease spreads through sneezes and coughs, and some pretty basic questions about the fluid dynamics associated with disease transmission are really not studied a lot because they're difficult to study and difficult to quantify. And actually, one of the effects of this disease is I think that there's probably more work that's going to be done in the next year than has been done in the previous 50 in these areas.
Mm-hmm. There were a couple super spreader events that I wanted to highlight in our presentation today. This is one that is well known. This is an event that occurred in Guangzhou, China. And there was a person here, and I'll illustrate with my little pointer here. There's a person sitting here who has COVID-19. Fairly small room. And over here on the right, you have an air conditioning system. Now, this is one of these wall mount air conditioning systems with inlet and outlet on the same device. This might be one that you put in the window of your home, for example. Air comes in the front, goes out the back. It's just exchanging, it's making it cool. Filtration here is fairly poor. They use fairly coarse material here for filtration. And look at the spread of the disease on this side of the room. These are all the people circled in red came out came down with the disease shortly after this primary index person got the disease. They concluded that, and Dr. Liu is with the equivalent of the CDC in China, we concluded this outbreak was prompted by the air conditioning ventilation. A direction of airflow was the primary cause, they believe. We cannot recommend monitoring temperature surveillance, increasing this, and improving ventilation. Ventilation keeps coming up in every one of these. This is another one. This occurred in Korea. Another interesting study. This again was done by effectively the CDC of South Korea. This was a 19-story building. There were call centers on floors 7 through 9. 11 floors of business above it was residential. On the 11th floor, which was a call center, they had 97 confirmed cases, 94 of them on that floor. Nearly all of them are on one side of the room. Look at this, they're all on one side of the room. So again, this is interesting in that HVAC system in effect there. The HVAC system is not unique probably to that floor. Certainly it's not unique to one half of that floor. And so it's not being transmitted that way, but there seems to be this transmission between the people in that location. So it didn't go anywhere else, stayed over there. Very, very local, considering that they're on, they're all in the same building. Now, I wanted to point out to you that for, every room, there is a design center in terms of air change rate, then the amount of air that needs to be changed per unit time. ASHRAE specifies this. ASHRAE, for those of you who don't know us, is the organization from which codes are set from. ASHRAE does the research and sets the specification, and then building codes are based off those specifications. So if you dig through a building code, at the end, you'll find ASHRAE documentation describing what needs to be done. In this case, we're talking about the number of changes per unit time. I didn't do the full list because it's quite long. I only went to the L's so that you could read it. But you see it's air change. It is the amount of air, the volume of air change per unit time, 4 to 6, for example, changes per hour here for the first one. It does change. You see that it goes up and down. This is correlated to the number of people, the size of the room, things like this. The thing is, though, here that I wanted to point out, not all rooms are well mixed. In other words, just because I have a change rate of 4 changes per hour doesn't mean that all the molecules in that room got exchanged. That depends on where the diffusers are, where the inlets and outlets are. So to illustrate that, we did a little CFD modeling. I own a company that does CFD modeling primarily in data center design. However, we also model fluid dynamics in rooms, often clean rooms, or for semiconductor, or we do office buildings, we've done casinos. Here we've taken an office that we actually work out of, and we've modeled the room with people in it and the air coming out. You can see the air coming out of the diffusers here. This is supply air, and it's colored by velocity. High velocity is green going up to red if it got that high. Blue is slow velocity. And you'll notice here that there's some dead spots, what we call dead spots. It's not getting everywhere. Now the returns are in the center of these devices. So it comes out here and it circulates, and I'm only showing you supply, not return. The return would go up into the center. But we wanted to show you, using a little bit more sophisticated 3D model, what this looks like so you can get a better view of that image. So here I'm using the software that we use is Ansys. And this is the Ansys viewer. And I'm hoping you can see this. Sometimes GoToMeeting doesn't always cooperate with me. But here you're seeing some vortices. So that's a dead zone over there. That means that that section of the room is not getting circulated or recirculated. It's not making its way back. We also have over here in this region, you see it's in the corner. It's between the flow coming out of these two. So this is probably dead over here too. If we move over here, we're going to see as well, not good mixing, not good distribution over here in this range. So this room is, although it's got the proper number of air changers per unit time, the mixing in it is not that good. Now, if we take a step further, here we're coloring it by velocity. Velocity is important because what velocity does is it tells you where the dead zones are. We do this a lot in clean rooms because we don't want any dead zones. For those of you in your home, you know where a dead zone is because that's where the dust always collects. It's these low pressure areas with very low velocity and everything accumulates there. And in a clean room, that's very important because you don't want to contaminate the semiconductor. So here we're operating at 0.3 feet of height and we're showing you a cut plane. That's what this is called, a contour plane. And we're showing you velocity as a function of color. The human eye can assimilate color very easily and assimilates information using color easily, so we use it a lot in CFD. So here, no velocity. Now, if I move up, you see it gets worse. Now I've got even more of a dead spot than I did before, over here and over here. And as I get to room level or get to human intake position, you can see that it's not good either. It gets worse. So even though the room is meeting the ASHRAE minimum specification for air changes, it's not meeting the total refresh that you would like to see, particularly if someone's emitting something through a vapor. Now, here in this animation, and I'm going to show you this in a moment, in black, I've got emission coming out of each of the people. So let's say they were sick and they were beginning to emit aerosol or particulate into the atmosphere. It was dry enough. Humidity is a big important issue here because, again, humidity, low humidity is causing these things to become aerosols easier and quicker. And so what you have is the emission coming out shown in black. What I'm going to show you in this animation is just emission from one person as it tracks over time. The animation sequence represents about an hour. This is a steady state condition. In other words, the air conditioning is on, the refresh is happening. It's happening in a steady state manner. The number of refreshers per unit time in this room are in fact within standards. But look what's happening. One person is emitting this vapor from their mouth in an aerosol form, and it's getting into everybody else's space because the ventilation in that room is not uniform. We're not getting a complete exchange out of that. This looks very much like what you're seeing in the call center case in Korea. So the point is that just because you have the proper number of air changes does not necessarily mean that you're going to eliminate the transmission of the disease. One other thing we did, we took the same office here and we colored it based on a cloud. We used a gas cloud. We assumed here that everybody was emitting something that was not desirable into the atmosphere. You see that the aerosol spread inside that office is getting to a concentration level of right around 50% of aerosol in the room. So this could be someone with COVID or a couple of people with COVID getting in the room. What we then did is said, what happens if you used local filtering? So here we put 6, and you can see them where my cursor is. You see these little boxes. These are 6 individual local HEPA filters, and we're running through them the air in the room, and you can see the concentration in that room dropped by 50%. So prior, we have a situation where the amount of concentration in the room, and again, I'm going to use a little 3D representation here to show this, and I'm going to use a contour plane. So this is a contour plane at 1 meter of height, same kind of thing I was showing before. These are concentration levels, 50% being about in the middle, and we normalized it so that it's in parts per million, but we normalized it so you could see it. So here in green, you see it's fairly high here, concentration of aerosol contaminant in the room. Now watch what happens when we put in the local filtering. The local filtering has a pronounced effect. It drops it way down. This assumed local HEPA filtering. HEPA is a high efficiency particulate arrestor. It's the same thing they use in clean rooms, and it's the same thing they use in other applications. Surgical facilities will use HEPA filters as well. Biological labs will use HEPA filters. And we drop the concentration down by 50% by putting 6 units in that room. This is the same effect you get in social distancing. What social distancing does for you is reduce the concentration of anything in the air by reducing the population. We happen to put HEPA filters in here. You could also reduce the population by 50% and get an equivalent outcome. So it's kind of interesting to see, and you can see those units are down here. They're a little low. They're about at seat height, or half a meter. But at 1 meter, you can see those concentrations drop dramatically. So I wanted to illustrate that using a little bit of CFD, just to show you that what CFD does for you. For those of you who don't know it, it stands for computational fluid dynamics, and it allows you to visualize the air and mathematically predict what's happening. I'm going to make one comment here about air change rates in airplanes as well, because this has come up a lot about airplanes. What about airplanes? Well, I was a senior executive at Fluent here in New Hampshire, and we did a lot of work with Boeing. I actually know the Boeing guys pretty well, or at least did. Passengers receive on average about 20 CFM, cubic feet per minute of air. The air change rate's quite high in an aircraft, 20 to 30 per hour. That's high. Furthermore, they use 50% outside air. In other words, they're pulling outside air. They're refreshing, and they're using outside refresh. They also use HEPA filters, and they use a very complex filtering system that takes the probability of removing 0.003 microns is almost 100%. So airplanes, the interior of an airplane from an air quality point of view is extremely high. And this bears out in the evidence. The first Canadian case of COVID-19 linked to air travel was by a patient who came from Wuhan to Guangzhou to Toronto on a 15-hour flight with 350 passengers on board. There was not a single SSE. No one got contaminated. And the great thing about airplanes is that they have a manifest, so you know who's on the airplane and you can track them. And they tracked them, and they saw no connection here. Now, you would think someone with coronavirus, COVID-19, on an airplane for 15 hours is going to contaminate other people. It did not. The only one we found was 1979 influenza. And this was not COVID-19, influenza happened in 1979. 54 people aboard an airplane sat on the ground for 3 hours. One person had influenza. Within 72 hours, 22 people had it. And then that even rose even higher after that. But the key point here, ventilation system was inoperative due to engine failure. No ventilation system. So this is an interesting data point. It's the only data point we have found in the airline business that shows contamination due to people being on an airplane itself. It seems highly correlated to the fact that they're using HEPA filters and they're refreshing that with 50% outside air. So I'm going to just put up a slide here in transition and give Dennis the floor. Position on HVAC and COVID-19 by the ASHRAE organization is the following. There is sufficient evidence, sufficient likelihood that airborne exposure to the virus should be controlled. Changes to the system, including heating, ventilation, air conditioning, should reduce airborne exposures. Ventilation and filtration are important and can reduce the risk through the air. Unconditioned spaces cause thermal stresses. You can read it yourself. The disabling of these systems is not recommended, but there are recommendations that are being made. And so I'd like to hand it over to Dennis here. And Dennis is going to take us through some work. He has been very much a part of this epidemic task force. He just participated in congressional briefings on this topic, and I'm thrilled to have him. Dennis, you want to take over?
Sure. Thank you, Paul. And thanks to everybody for attending today. Just a little bit of background on the ASHRAE Epidemic Task Force. Around the week of February 24th, Paul mentioned I am chair of Technology Council this year, and we have a group called the Environmental Health Committee that is responsible for developing ASHRAE's position documents and emerging issues brief. We've had a position document on airborne infectious disease since about 2001, and it was in the process of being updated when this all broke loose. We had a position document committee that was formed well over a year ago before COVID was on our radar. And it came up in Orlando for a vote for approval, and some editorial things kept it from being approved. in February, when things started shutting down, we realized that it was important for ASHRAE in the world for us to get that new position document out. We changed its name to the infectious aerosols position document, and pulled the committee together, worked nights, weekends, holidays, and got the position document corrected and voted on by the board for approval in April. At the same time, I charged the Environmental Health Committee with standing up an epidemic task force to look at all of our current guidance, what we say in the position document, and also look at our standards and start developing current guidance on shutting down buildings, reopening buildings. Let me, let's see. I am not able to advance my slides here.
I got it.
All right, so I'll just talk.
Yep.
So we formed the committee, and the Environmental Health Committee is made up of groups from various technical committees throughout society that develop our standards. ASHRAE 90.1, ASHRAE 62, which is the ventilation standard, 55 is the comfort standard, and many others. 52, our filtration standard. We brought in technical committee chairs and subject matter experts. We have a person from the CDC through NIOSH, Dr. Steve Taylor, interestingly enough, they're not related, but Stephanie Taylor at Harvard Med School, MD there, who is an expert in infectious disease, along with our technical committee experts. We have about 17 people on the committee, including ASHRAE staff, and we're around about 12, broken up into 12 teams. Those 12 teams have about 10 people, 10 other volunteers. So the committee outside the core of 12 is about 125 people working. And we have worked literally on some 5, 6, 7, 8 hour calls and 3, 4, 5 calls a week since February 24th to pull together the guidance, redo the website. The first thing we did was open the website up and a lot of our documents for free view. First time ASHRAE's ever done that. And just to give you an idea, the year ending January 2019, we had 806,000 media impressions of our website, which is people coming to the website or ASHRAE's name being put in front of them. Since the first week of March until now, the ASHRAE website, and specifically the COVID page, has had over 550 million media impressions. So more than ASHRAE's website's ever seen in the entire life of ASHRAE. So we're, like I said, we're organized around these key components to develop detailed guidance in the areas of healthcare, commercial buildings, K through 12 universities, residential transportation, filtration and air cleaning, and building readiness. And Paul, you can go to the next slide. So we started with get the position document approved, create those 2 statements that were our guiding principles, that transmission is likely through the air and that the HVAC systems can be used. Paul mentioned the role in transmission, but also properly working HVAC systems can be used to help mitigate as part of an overall strategy the transmission of COVID-19 and infectious aerosols. So, do no harm. We started out looking at increase the amount of clean outside air being supplied to buildings. Some of our early recommendations that have been backed off a little bit was to ventilate 24/7 at as close to 100% outside air as you could. But that's not our recommendations, as we've got some lessons learned. Increase efficiency of filtration to MERV 13 or better. Go to 14 where possible. And you can see from Paul's dramatizations and all that, the better the filtration, those HEPA filters are good. MERV 13 is actually the first level of filtration that's able to begin having some efficiency ratings at 3 microns. And we hear a lot about 0.5.
We should define MERV for them too, Dennis. A
Yeah,
minimum
so
effective rating.
Yeah, it's called the minimum efficiency reporting value, and it's based on ASHRAE standard. Goes from 6 through 16, and then of course HEPA filters. Let's see, I may have a table right here on my other screen. I can get it up for a second. But MERV 1 through 4, you don't see many of those. I mean, their minimum particle size efficiency is 10 microns, which is pretty big. And the 5 through 8s are 10 microns down to 3. 9 to 12 get you some efficiency at 3 to 1 microns, and then 13 to 16 are the 1 to 3 microns. I mean, starting to get into the sizes of some of these larger droplets, not of course the molecular level of some of these, but your standard, if you look at ASHRAE 62, the minimum efficiency, you either have to have clean outside air equal to, or your filtered recirculation air is MERV 8, which is what you typically see in a lot of buildings these days. And then if clean air, I mean, if clean outside air or increased outside air and increased efficiency couldn't be had because of system limitations, then start looking at air cleaning technologies, disinfection, such as upper room UV, and then supplement those systems where things like Paul pointed out, you don't get good mixing and you don't have good filtration with portable HEPA filter units and portable UV. Next slide. So this, so on the congressional briefing, Dr. Bill Bonfleth, who is chair of the committee, chair of our epidemic task force, he's at Penn State. He used a slide in our congressional briefing just to kind of demonstrate there's a lot of work being done. I don't know if anybody knows Joe Allen at the T.H. Chan School of Public Health at Harvard, but he just released a book called Healthy Buildings, kind of his life's work with actually monetizing the benefits of good indoor air quality. So, you know, even absent infectious disease, I mean, some of this work, these were Canadian researchers back in 2015, did some work and just showing that, you know, the impacts on health and mortality rates improve with the higher, showing over on the left the standard range of filters and HVAC units, and then the benefits of potentially going to a higher standard, a 13 or a 14. And you can see there with the list of cities, the bigger benefits are had, of course, in areas of the world where we know outside air is not that great. But in the slide on the right, the London slide actually shows a city that might be as typical or more typical of, you know, some cities, bigger cities in the U.S., and even there up to, you know, $180 a year in benefits to people from mortality rate, morbidity benefits for a fairly low investment and energy penalty to going to a better filter. That's just in avoided healthcare costs, days, sick days, those kind of things. So those can be beneficial to the building users, which sometimes is in conflict with the building owner, but it's also good for a business owner from a monetary standpoint. The more productive and the more healthy their workers are and on the job for more hours, the better the bottom line. And often that's very hard to monetize when you're talking about improving this.
One of the issues here as well is as we make these buildings more energy efficient, we're tightening up that building envelope. And so there's more need, I would argue, for improved filtering and ventilation in these rooms than ever before. Wouldn't you agree?
Absolutely. And if you go looking at, especially up in your part of the country where you have some fairly long seasons of low humidity, and we're talking about maintaining humidity ranges anywhere from the 40 to 60% range, you start thinking about having to maybe humidify buildings in the future. Building envelope is critical in those colder climates. Well, it's critical here in hot and humid climate as well for leakage, but critical in your climate to avoid condensation and structural damage and things like that in those harsh winter conditions as well. So a lot of work. I think there's a lot of opportunities being made available to us that, we just don't know what we don't know, and are beginning to learn about, what better buildings and better HVAC systems can do for us from a personal health standpoint, and then from a disaster mitigation standpoint. You can go to the next one. So we focused on 3 key areas: shutting down buildings, reopening buildings, and then operation of buildings as we start to reopen in the various phases outlined in Opening Up America, which, the first phase is somewhat, or phase 2, this kind of partial reopening. I just wanted to show, Paul showed, fairly decent air distribution in an office setting, but I do a lot of work with school districts here. Now my local school district, they have about 85 buildings, about 14 million square feet, about 65,000 students. But I mean, the buildings range from 1956 to being completed, some of them being completed now. A fair chunk of that inventory is older buildings. And this is a typical classroom. About 1% of the classrooms in the district are this. There are about 1,400 of these sitting in the district. We call them wall-hung heat pumps. Often they have little to no outdoor air. Let's see if my pointer works. Can you see it?
No, but I know here's the inlet outlet right up here, right?
Yeah, and then the outdoor, if you look at that little smaller picture down in the lower left, the outdoor intake's right there over to the left, right above the condenser section, And often that's usually just a hole in the side of the unit with a backdraft damper on it. And they're designed to provide around 900 CFM, 240 CFM of outside air. If that was ideal, but many times that flap's rusted shut. We're in a coastal environment, high salt air content. But you can see, on paper, they look good. 9.5 air changes an hour. If you look at Paul's table, from 6 to 20 for a classroom, and 1.5 air changes an hour of outside air. But a lot of times there's none. So tomorrow I'm actually going out with the district to look at, we have about 3 types of those with just an outdoor intake, some with a little enthalpy wheel in them, and then some that serve, some that are ducted. And we're going to do some tests and see, how much we need to do when students come back. We've been, of course, recommending no more than 50% occupancy in the room, and possibly going to the HEPA filter, portable HEPA filters as well, social distancing and additional filters. We do get a fairly decent filter in these. We've got MERV 9s. That's about as good as they will take and still function properly. But I just wanted to give everybody kind of a real world application, and most of that circulation is in the back. It's very similar to that Guangzhou restaurant, that you've got horizontal airflow cascading from person to person, which is absolutely not ideal. Go ahead.
A couple of points here, Dennis. One is that these units originally were probably put in place to modulate temperature. And in doing so, they're okay. Cold air does transfer heat across the room at some point. But if you're depending on them as well for filtration, that changes the game quite a bit, because of the issue of these dead zones where you don't have good mixing in the room.
Right. All right, so keeping on with the key concepts, very early on, I mean, we made sure before we even got the teams to generate what's on the website as guidance documents, we put up some frequently asked questions that we actually made up ourselves, questions that we would have as building designers, operators, and service providers. And one was just, no matter what, when you unoccupy a building, we do not recommend that systems be shut down completely. At least go into unoccupied setback, maintain some reasonable temperatures, humidities in buildings, and let the ventilation systems run on at least on an occasional basis, just to refresh the air in the building. 2 is improve efficiency when existing is deficient, when possible, and you can stand the pressure drop, increase outdoor air rates as we talked about, and then apply cleaning and disinfection. But the other thing is monitor continuously. You can go to the next slide, Paul, if you like. So we always believe that local engineers, local service providers, people that know your climate zone, your buildings, how they operate, you should stick with your team and look at your original design documents, test and balance reports, and your engineers of record when possible. Use a commissioning provider, in-house or third party. If you got people on your staff that know how to use instrumentation and monitor the building automation system, and just to verify that your systems are working and that the equipment's functioning. Verify your contract roles and responsibilities when you're starting to shut a system down. Review your force majeure clauses to make sure you're not going to be left with no service provider during a shutdown. And then work with vendors to make sure they have supplies on hand should equipment fail, so you can get that equipment back up and running as soon as possible. Next slide, Paul. So something that we all should do, but I know from working with building owners now, this is 46 years and my 40th year in ASHRAE, that building owners outside of fairly large, well-funded private portfolios and some government agencies that not always are HVAC maintenance at the top of the list. Even for years here before we got involved a few years ago, the school board didn't allocate but about a nickel a square foot for facility maintenance. That was all facility maintenance, not just HVAC, and it should have been in the order of 45, 50 cents a square foot. And we've gotten there by getting an additional 1 cent tax here in the county to help us with that. But document deficiencies, whether your BAS is tracking them, find out where you're at, develop a repair plan, get systems working properly, and then really look at sequences of operation, normal mode, unoccupied, occupied. Get your BAS system provider to create an emergency shutdown plan. So so that it's just a one key operation or a schedule override to put you into the setback that you need to keep your buildings operating and keep their indoor conditions healthy even when people aren't in there. And then have a plan for starting back up after an event or reoccupancy. Go ahead, Paul. When you're talking about building automation systems, if you've got a large portfolio, you've got a district-wide or a city-wide or campus-wide system, one key thing is before you do anything in any kind of disaster, print out your current set points, your adjustable values, get a hard copy PDF, store those on site in the cloud, perform a complete backup of your software and store it somewhere. And then depending on how you get relocated or people get relocated, set up and verify that your remote access is working and you're able to log in and monitor conditions. Next slide. Walk the facility with your stakeholders. I mean, that could be your insurers, legal counsel, your local state, your state office of school facilities, or whoever that might be. Collaborate with them. Come up with a plan, both for modifications and then make small changes at a time. This is kind of consistent with our guidance. And then monitor. Keep very good records. You never know where due diligence will take you, and depending on in states where I know for engineers here in the state, statutes of limitation are 8 years, and I don't know about many of you, but remembering what I did last week at a certain time sometimes can be challenging, and if you don't have good records, but trying to remember what you did 8 years ago is near impossible unless you've really kept good records of what you're doing. Next slide, Paul. After an event occurs, analyze all the changes you made and the outcomes for insight into success. It's kind of what we're doing now as we've gotten guidance posted, and we're going through and doing a QA review to make sure all the teams are giving consistent guidance. Some lessons learned. We've created a parking lot for technical council, our technical advisory committee, our research advisory committee, the board of directors on the future of ASHRAE, future of HVAC, how we can help protect health, safety, and welfare. Health and wellness are in its early stages of becoming what some of the lead and the energy efficiency and high performance building standards were 20 years ago now. Where consumers and building users are beginning to become aware that the indoor environment in buildings can help or hinder your performance and your overall well-being. So update emergency preparedness plans, based on these kind of events, and capitalize on your lessons learned. School of Hard Knocks is still a very large university. Update your project requirements. We are working again with a couple of universities and local school districts on, how can they operate at higher outdoor air rates? We need research on what those optimums are. Definitely, I think we've shown and demonstrated that higher efficiency filters are a good bang for the buck. Again, if you don't consider even infectious aerosol control, but controlling 2.5 to 2 PM 2.5 PM10 micron particles just helps people with asthma, with respiratory problems, other health compromising situations, reduces. I think there've been several studies that show it reduces sick days and absenteeism. And improves people's cognitive function with better fresh air and higher filtration. Tighter duct and damper sealing standards, and then possibly better monitoring and record keeping and control. Paul? That's kind of the end of the presentation, but I think part of the most beneficial is going to be the conversation. So.
That's right. And Jonathan, one of the articles that you referenced in your piece, and I encourage people, by the way, links to many of these references are in the transmission that I sent out, the invite, but also I'll put them on the ASHRAE, the New Hampshire ASHRAE website. One of the studies coming out of—
put a link to the maybe on the question slide, put a link to the ASHRAE COVID resource page. And then the other thing I would encourage is right at the top of the page is a email address, which is covid19@ashrae.org. And that's covid-19@ashrae.org. If you send a question, there is a person on staff that gets those. We've answered almost 400 now from engineers to the general public. But if you send a question, our goal is to get it to an expert within ASHRAE, not just a member of the task force. But somebody that is a subject matter expert around your question, and get you an answer within about 24 hours. That's our goal. Some take a little longer, especially if we have to run down an expert in a fairly narrow field. But that email address right there gets you straight to a staff person that screens every email that comes in, sends it to myself, Bill Bonflip, the chair, and then we convene and kind of talk about who we think's the best, either on the task force or within our technical committees, and well over 100 technical committees working on ASHRAE standards and ASHRAE handbook chapters to run with some of these questions and get them answered for you.
Now, there's quite a bit of interesting work going on here in the research of this material, and I want to just point out a little bit of it here. Now, some of this work that you were doing, I believe, Jonathan, had to do with some of the transmission mediums. Do you want to review some of that with us? Will I take some questions here?
Sure. I mean, my own research was motivated by the fact that, in contrast to the discussion that's taking place here, which is clearly among experts who understand how infectious disease might spread through airflow, the vast majority of the discourse I was seeing journalistically sort of treated COVID-19 like magic fairy dust. And, you know, there were articles about, you know, how much bleach should I use when I wipe down my Amazon packages? And I think some of the confusion is understandable because there are diseases out there that do almost seem to transmit themselves by magic, like measles is an example of a disease that just, you could be standing in the same room with somebody with measles, and if you're unvaccinated, you can get the disease. COVID-19 does not seem to be a disease like that. It seems to be a little bit more predictable in the way it passes from one person to the other. But journalistically and even in scientific literature, I saw relatively little exploration of the actual behaviors that tended to spread the disease. And even now, when we read the media, we see so much focus on the political aspects of it, lockdown, whatever Donald Trump said yesterday, and it isn't a scientifically helpful discussion. And I think the challenge for experts like you guys is often to penetrate that noise and to get out the message that, look, there are concrete steps you can take to make work environments safer. And it isn't just about wearing masks and staying 6 feet apart. That in some situations, that's obviously part of it. In my own research, sorry, go ahead.
I think the 6 feet apart is all understandable. Someone sneezes on you or coughs on you, particularly if you're vertically challenged, you've been a recipient of feeling like you need to go take a shower after a conversation with somebody, right? I think we get that. The newer one is the aerosol transmission, particularly from people who are asymptomatic. This is the sort of the catch, is you don't know you're sick because you're asymptomatic, and the possibility of transmission through aerosol exists. In fact, you categorized it into 3 possible transmission sort of groups, correct? You want to review those?
Yeah, and so just in terms of asymptomatic transmission, because my focus is on super spreaders, I looked at some of these people who are asymptomatic. There's a famous case study that played out in Korea. There was a large megachurch there, and there was a particular woman, I think she's referred to as patient 31. I think if you Google patient 31 in Korea, you can see her case. Reuters did a huge piece on her. And yes, and she went out to lunch, and she went here and she went there, and she infected a lot of people. If you look at the way scientists talk about the disease, there's 3 main vectors they talked about. They talked about infected surfaces, which is sometimes called fomites. They talked about large droplet transmission, whereby the disease is transmitted ballistically through large droplets that tend to emit from your mouth and nose. We've all seen these disgusting videos, disgusting but necessary to watch, where actually you can actually see these large droplets. It's Newtonian mechanics, and that's where distancing makes the most sense. That's sometimes known as large droplet transmission. And then you have small droplet transmission or aerosol transmission. It goes by different names in the literature, where you have very small droplets that can remain in the air for minutes or even hours. They drift around. And there's some complex stuff there because virologists still aren't sure what part of the throat or the nose, the respiratory tract, the disease is most likely to lodge itself, and that affects their analysis of what kind of particles are the most important. But the public health responses to these different transmissions is radically different. If this were a disease that was primarily transmitted through infected surfaces, which we now know it isn't because the CDC has told us it isn't, our public health response would focus on obsessive wipe downs of surfaces with bleach, which is what a lot of people do and for some reason continue to do. If it were large droplet transmission, and there does seem, my research suggests there does seem to be a huge amount of large droplet transmission, you would expect to see, as we do, a huge prevalence of super spreader events at things like sports events where everyone's screaming in each other's faces, singing events, and tragically there are a lot of singing groups that have all infected each other because when you sing, the muzzle velocity, when you speak, the breath coming out of your mouth is much higher and the droplet size is larger and the droplets go further at greater velocity. Funerals where people are grieving, very emotional scenes. These are the kind of super spreader events I saw and are highly consistent with large droplet transmission. And in some cases those large droplet transmission can be inhibited or accelerated according to the pattern of airflow, as we saw in the Guangzhou example that you led off with when you talked about that restaurant in Guangzhou, China, where they superimposed an airflow map over a map of the people in the restaurant who got ill. And then, of course, in terms of small droplet or aerosolized or the transmission, because in those cases, as your computer model shows, you have small particles that are going to drift around according to air currents. Even when there are no air currents, the normal process of gas diffusion and natural convection, you're going to get some long distance movement of these particles, and staying 6 feet away may not help you. And it's all about controlling airflow and air quality on a room by room or building by building level and eliminating dead spots, as you've emphasized. So these are three very different kind of public health responses. We now know surfaces are not a major contributor. My research suggests that direct ballistic transmission of large droplets is a huge contributor. Certainly there has to be more research to determine the level of contribution of small particle aerosolized particles. How is that affecting? I'd say of all three of the mechanisms I've just described, there's the most amount of uncertainty about that one because yes. I haven't seen any systematic study of it.
Yes, and it keeps popping up. You pointed this to me yesterday in our preview of this webinar and rehearsal for it. You pointed me at this one. This one came out of Germany. This is a virologist who's saying ventilation is the most important thing you can do. This is someone who he's German and is talking about ventilation and the risk of aerosol transmission through ventilation. I wanted to point out one other study. I don't know if you had a chance to read this particular study. I'm gonna try to drag it over here as soon as I can grab it. This one was done out of the School of London Health. This is I believe the dynamics of controlling droplet and aerosol transmission. Imperial College, together with Penn State. They studied a high school in this case and did quite a bit of detail on ventilation in this case. I wanted to just point out here that look at this last sentence. We're bringing ventilation to the recommended levels. Again, air change time, per hour, bringing it up, and they reference ASHRAE. Bringing it up to ASHRAE levels had the same mitigating effect as vaccinating 50 to 60% of the population. That's incredible, if you ask me.
Yeah, now
that was influenza, but yeah. Nonetheless, similar idea.
Well, so you say nonetheless, but this goes back to some of the data you were showing about the more general benefits that flow from better ventilation and airflow in buildings. As has been emphasized by people in the debate about COVID-19, influenza itself kills tens of thousands of Americans and hundreds of thousands and maybe even millions of people around the world every year. So if you're looking at engineering solutions that are addressed on an urgent basis because of fears about COVID-19, it's not as if that technology and those upgrades aren't also going to have a positive benefit effect for all these other infectious diseases.
Exactly.
In fact, my speculation has been that this will be the first pandemic in the history of humankind, which results in the medium term of an improvement in public health, because the same measures that we're taking, and not just in regard to airflow, but in regard to everything we do, examining our behaviors in all kinds of contexts, are going to suppress the transmission of dozens of other diseases, including influenza, which also exact a very high death toll.
I got a question coming in here. I'm going to pass this one over to you, Dennis. What would displacement ventilation do? Would it be a better means to control small droplet transmission?
I saw that question. I mean, I guess I have to be careful here. I'm not speaking on behalf of ASHRAE because we don't really have a position on it yet. I guess my concern with displacement ventilation in the traditional sense of what I'm used to is providing your ventilation air low in the space and then returning toward the ceiling, almost like underfloor air distribution. And with the large droplets falling and as they dry, I don't know. I personally feel like we need to study it. Is it going to push more particles back up into the breathing zone than it's there to displace? So I mean, quick answer is I don't know. And my gut reaction is that it may not be a solution. It could be, but I think we need to do some more research on it. But my first gut reaction is it feels like it wouldn't be a great application.
I think you would agree there's probably a variety of strategies that might work. And for example, what we do in clean rooms for semiconductor, we manipulate the geometry of the inlets and outlets and the geometry of stuff in the room to optimize it for clean air. We're trying to make sure there's no collection. And it's a similar strategy here to try to take inlets and outlets in a room and position them so that you have the minimum amount of dead zones or dead spaces or no air travel zones, and try to mix that room as best you possibly can. Wouldn't you agree?
Well, that and what's not near possible in commercial type buildings is, and maybe we need to rethink this, is the idea like we do in healthcare is try to arrange that air distribution where air flows from clean to dirty. Mm-hmm. And you're always controlling that direction of airflow, mm-hmm. which is the same principle, designing air outlets and air inlets to get a desired outcome, right?
Mm-hmm. Yes. Well, all right. Well, we're a little bit over the time. I think we've answered most of the questions. There is one about how long the coronavirus can stay active as an aerosol. I don't know the answer to that. We're not virologists here, and I don't think, Jonathan, you probably have more information on this than anybody. You've been researching it. I don't think we know much about its life, do we, in terms of how quickly it dies?
Well, I'll just say two things. One is that often virologists will speak of the I believe minimum infectious dose. I'm probably butchering that, but basically it's like, what is the critical mass of the virus that you have to get exposed to in order to get sick? And so obviously, the more of it you get, the more you're going to get sick by. In terms of how long these things last, it's very deceptive, because what happens is people have read these articles that say, oh, it lasts on surfaces for a week or 2 weeks or 3 weeks. That is true based on PCR testing, but the critical thing is, how long does it survive in a form that it can be then taken and cultured in a Petri dish? That, that's when you have to worry, because if it can be cultured, then that's obviously something that can infect you. And when you take that as the benchmark, the numbers go down from like 2 weeks to a day or two, right? I'm not a virologist, but I have seen detailed comparisons of the different testing methods. And so when people are discussing this, the first thing I look at is, what is your litmus test? If it's just, can a scanner pick up molecular indicators of the presence of the virus, I'm not interested in that. I'm interested in, can you culture it? And that, I think, is the important benchmark that lay people should be looking at in terms of public health and worrying about whether the presence of the virus can infect them.
So, John, if you were to give advice, which you probably do, to your significant other or friends, based on your research of super spreader events, what advice would you give? Not from a science necessarily point of view, but just researching the data. What would you recommend?
So I'll be honest with you, it's very hard to convince people of any course of action based on the science, because people typically do what their neighbors do, or they typically do what their kid's teacher told them to do. People defer to authority figures, and frankly, that's probably a good thing, because I think if people followed the advice of everything that they saw on TV or on Twitter or in their inbox, they'd be doing some pretty crazy things. Mm-hmm. However, the one thing that I find is always the most direct and persuasive way is the power of video. And you showed some of the videos before, including some video which was done out of, actually, I believe it was the mechanical engineering department of, forget which university, but a lot of this work is being done by engineers and not by public health officials. The video from the lab in MIT that you referenced, Lydia's lab, those videos, sometimes it just takes 5 minutes to watch, but when people see the way the particles flow, especially when people sneeze or cough or talk in an animated way, that leaves a huge impression. And in fact, and I tell people, there's some really common sense things you can do. You watch the video, if you're talking to someone, as well as abiding by all applicable regulations, talking softer, talking downward, just avoiding generating particles. You can still communicate with somebody while minimizing the amount of particles that you put into the air. These are really common sense things, and I think a lot of the video that's out there, some of which you showed, can be very persuasive in that regard.
You're absolutely right, and actually orientation too. Or you don't orient. I know people like to be looked in the eye, but don't orientate yourself directly in front of somebody. Offsetting furniture layout and orientation is a big deal too.
Yeah, and I don't know why people don't talk about it. It's such a simple thing, and yet people don't talk about that.
Well, I want to thank you both for attending today. It's been a fascinating session, and I tried to answer all the questions. There have been a couple questions coming in about if we are going to make handouts available and so forth. Yes, the answer is qualified yes, of course, but I can't quite do the animations that way. They're just too big. But we did record the entire event, and that will be available. You will get an email from us, and I'm just going to put up here Lydia's page. Lydia Bariba, if you don't know Lydia, I mean, she's a McGill University mechanical engineering fluid dynamicist and working also in Harvard Medical. She's got a group at MIT right now. There's very, very fascinating work going on here. There's a TED Talk she's done. I'd encourage you to spend a little time there if you have it. It's just fantastic work that she's doing in the intersection of science and medicine, or I'd say in this case, computational fluid mechanics and medicine. This program we will provide to you as a link. You can download an MP4 or you can just view it. In addition, if you want a copy of the slides, I can certainly provide them in a similar place and give you a link to download them, probably as a PDF, because size gets to be an issue with all this graphics in it. So I want to thank everybody again for being here today. I want to thank Dennis and John for joining me on this event, and I thank you all for attending. If you have any questions, please send me a note. I will try to answer them for you if we didn't get to it earlier. Thank you very much.
Thank you.
Thank you, Paul. Thank you, Jonathan.
Thank you.